did, well, I did to Houston Organic Geochemistry Society, which was really just sort of more of a technical overview than a sort of example of what Girasol can do, but it's probably not a bad one to start to get you sort of into what the program does. So that's just some very nice pictures of myself and Julian. So I don't know what you thought about Wellsite gases. So Wellsite gases for me that we measure in Girasol are essentially those that are released when you drill a volume of rock. Yeah, there are sort of several other ways to add gases to the mud system. You can obviously take influxes. So if you drill under balance, you get a flow into the wellbore. Now, that doesn't necessarily mean it's large amounts of flow, so it doesn't have to be a kick, and that will affect your gases. Or you can drill slightly over balance relative to a fracture pressure and sort of initiate fractures, and then you obviously get a flow. As you drop the pressure that you're circulating with, so if you make a connection and you drop what would be the effective circulating density, then you get a little flow back into the well. So for those of you who may not be familiar with wells, typically if you're doing a well, you'll have a mud weight. It'll be a static mud weight, and that's designed to balance off the formation pressures. Once you turn the pumps on, there you require a certain amount of pressure in the system to actually be able to flow the mud round through the drill bit and back up to surface and carry all the cuttings load, and that adds a small amount of pressure to the system, so it effectively increases the mud weight. So when you make a connection or you take off that circulation, you get a little drop in pressure, and you often see that if you're close to balance or you're slightly over balance relative fracture, you often see a gas that's associated with that drop in pressure when you recirculate the surface. So that's what sort of connection gases are. So it's been around for quite a long time. We've been doing, people have been measuring Wellsite gases probably since the 50s. And, they've had basic Wellsite GCs probably that long, and digital data is around certainly for the sort of last 20 to 30 years. Okay, so, and here's, I don't know how many of you have sort of seen mud logs. So here's what you commonly get, and on the sort of left-hand side, there's really a very basic. Well, so in most basic descriptions on a mud log, you might be looking at wireline logs. You'll usually get ROP or some measure. You'll get a total gas, and you'll get a chromatographic. You get a C1 through to C5s, or if you're in the more sophisticated system, you might get anything up to C8s. And you'll get a lith description, you'll get a lith column, and you usually get some basic sort of data. What's the mud weight, what they did to the well, where they changed bits, if they got any connection gases, it's often recorded on here. So all those kind of basic things, but no real interpretation. It's just a presentation of the data, if you like. On the right hand side, there's this is a well that was just drilled actually with flare, and so now you've got a more complex system. Usually on a flare system, you're usually monitoring a gas in to the wellbore at the suction pit, which is just before the mud pumps, and you're using measuring a gas out, which is usually, if they can do it on flare, it's a probe, and it's as close to flow line as they can get it. And in those, you'll see in those ones, now you're starting to pick up wireline logs, you've got a lith column. The primary use of flare, though, is really to sort of distinguish different fluid characteristics in the reservoir. So what they tend to do is just break it up into like a fascist description of fluids. They often don't indicate where they think pay is, and they don't really describe the fluids necessarily in terms of a composition. So is it a gas? Well, is it gas? Is it an oil? Is it and especially what's its likely GOR likely to be? So you've got this data, but it doesn't really get worked to death. Yeah, it sort of plays second fiddle, if you like. It's to petrophysics on a well in terms of identifying pay. Now, petrophysics will identify pay for common wireline logs. It won't necessarily identify the nature of the fluid. unless you run a sampling routine on it, or unless you do, well, you can do two things. You can either do a pressure analysis, and the density of the fluid will give you some idea about its composition. So if you get a density of a fluid, you can usually back calculate a CGR and a GOR if you make some assumptions about API. But if you've got PVT modules that'll do that, if you run if you're running a pressure sample, running a pressure tool, you usually put samples on it, so you can actually physically take samples of the fluid. So, here's a sort of cartoon of a well. So what typically happens? Well, what happens is you're obviously going to drill your section. You're going to circulate those cuttings back to surface. The gas that's entrapped in those cuttings, as it comes back to surface, will gradually come out of the rock. It probably can go to solution. Certainly in oil-based muds, might be a debate about whether it stays in solution in water-based muds as it gets close to surface. It'll go to surface. It comes down. The mud comes out of a flow line. Usually, you've got a gas trap. If you've got a sort of simple floating gas trap, so a simple floating gas trap is really just something that floats in what's called the possum belly. So the possum belly usually is a big tank of mud that sits before the shakers, and the shakers take out the cuttings. And that trap it's got an agitator in, and it circulates a fixed volume of mud relative to a fixed volume of air that flows around the sensor, and then that air that's going through there's a suction line out usually to a mud logging unit or a remote sensor. It can be one or the other, and in there there'll be usually all your gas analysis equipment. So usually, if it's set up, there's two types of sensor. There's one that'll measure a constant methane equivalent, so a total gas, and that measures a constant methane equivalent. It's an FID sensor usually, but it can be a thermal conductivity sensor. And it's supposed to measure a total methane equivalent unit of gas. And that's pretty much sampled constantly. And then attached to that line, there'll be a little splitter that takes a sample off anywhere from sort of every 45 to every 90 seconds. And that goes to a GC, and the GC separates out the components. The most common sort of set is to separate it out into C1 to C5, and usually a C6 plus. But you can get more complex setups now that'll do C1 to C8s commonly, and they measure aromatics as well as alkanes. Obviously, once you start to get past about C5, C6, you start to get a lot of different compounds. So you're not usually measuring everything that's there. You're just measuring either a select group of compounds or groups of compounds sort of grouped together. Yep. You can replace the GC with GCMS. That allows you to look at non-hydrocarbons. It's not easy to look at non-hydrocarbons. Well, it's not possible to look at non-hydrocarbons on a typical FID sensor. If you wanted to look at, say, sulfur compounds or nitrogen compounds, you have to set up specific detectors on the GC. GCMS, obviously, you can measure. You just measure by mass usually. So you can measure. You can measure helium, hydrogen, carbon dioxide, hydrogen sulfide, anything you want that you can distinguish quite clearly on mass terms, and on a GC from hydrocarbons. Usually that's the most common setup. There are others. There's detectors. A lot of people now, well, certainly several companies are marketing semi-permeable membrane detectors. So that's like a little probe. You pass air through it. It's got a semi-permeable membrane that allows the gas to diffuse across the membrane out of the mud. And you same as normal gas traps, you take that flow of air back to a GC, and you measure the total gas and a GC and a composition. So they're all pretty much doing the same thing, really. So I don't know if you guys have ever thought what it's all related to. So things that affects the sort of, so what you're in effect measuring at surface is you've got a fixed volume of mud that's dilute that releases gas, and it's taken into a fixed volume of air, and you measure a concentration in that air. Yeah. There's a couple of things implicit in that. That means if you change the rate of airflow relative to the mud flow, you'll get a different reading. You don't get the same relative amounts, but you get a different reading. So effectively what you're trying to do is degas a fixed volume of flow rate, so a fixed volume per unit of time of mud. So if you sort of keep that in mind, what you're going to think about when you're drilling is what's happening is you're breaking up a fixed volume of rock, in meters cubed per minute, and you're placing all the gas out of that unit of rock into a volume of mud that's determined by your flow rate. So if you think about it, your fixed volume of mud, really that's ROP, hole size, are the two things that really affect that, And then the other one obviously is going to be flow rate, because flow rate determines how much mud flow rate then determines how much mud you put that, how much volume of mud you put that gas into, So what that obviously means is that if you drill faster, but you don't change the flow rate, you're going to get more gas volume per unit of mud. Similarly, so if you drill at the same rate and you change the mud flow rate, so they say increase the mud flow rate, you're going to dilute the gas per unit volume of mud. So you need to take account of those when you're actually thinking about your gases. And the way we do that is this normalization procedure. And that what the normalization procedure does is it basically just takes, it says, right, I'm drilling so much volume of rock per minute. I'm putting that into, and what I'm doing is I'm putting that into a certain unit volume of mud, and that's how and if I change those ROP, those volume of rock, or the volume of mud parameters, then I change the actual total gas amount into which we call then the normalized gas. If you think about it, when you're drilling your rock volume of mud, really the bulk of the gas is probably going to be held, especially if you're drilling through sort of reservoir sections, it's going to be held as free gas in a pore volume, and therefore, the amount of gas that you liberate is going to be a function of the porosity, really times the hydrocarbon saturation. There's going to be some modification for GOR, because obviously there's more gas associated with the gas in the gas accumulation. For instance, there is an oil accumulation, and the higher you make the GOR of an oil accumulation, the more gas you should get to surface. So it's a factor of all those things. There's usually gas in most rocks. There's certainly always a little amount dissolved in water. And if you think about if you've got a mudstone, then if you've got a mudstone, you initially it's got some organic content. And most mudstones have got some organic content. They might not be salt rocks, but they've got some organic content. Then, you're going to generate a little bit of biogenic gas early on. And as you start to get hotter and hotter and hotter, the organic material that's in the rocks is going to start to generate in situ gases. So it's very rare that you find a gas without any, you find a rock without any gases in. Carbonates carbonates are often, especially if they're clear pore and organic pore, are often as close as you're going to get to a rock without hydrocarbons in, and that's assuming that you've flowed no material through there. So obviously, if you're at the crest of accumulation and you're leaking, then even in a carbonate, you're going to get some flow through the pore volume potentially. Okay, so the other thing you need to bear in mind with sort of gases is that this is true, especially if you're in oil-based mud systems, but it's also true in any mud system where there's a lot of organic material in the mud. So if you've got a lot of, say, polymers in a water-based mud, or you add a lot of diesel to a water-based mud, then what happens is that well, a couple of things. One, you can take more material into solution. So if you look at this slide, the top sort of right-hand graph gives you an idea of how much material you can take into solution for the pressures down a well based on a water-based and an oil-based mud system. So you can see in that, theoretically, you could take pretty much all the gas you drill from a rock. I've sort of highlighted in there what the sort of typical gas volume from a volume of rock drilled is in the red and the blue. And you can pretty much take all that into solution in oil-based mud. And even in a water-based mud, you can take quite a lot of it in solution. The only thing in a water-based mud is it will tend to come out of solution before you get to the wellhead. Little graph there on the bottom. I haven't been able to find much. This is just a literature search that I did. It's not easy to find individual compounds in oil-based muds, so I've taken solubility of gases in hexadecane as a proxy. So that's a C16 alkane, and just at 1 atmosphere pressure. And a couple of things you can see on that one, that obviously the higher molecular weight, so they think that's got C1 to C4 on, higher molecular weight compounds are much more soluble. And as you get to higher temperatures, their solubility decreases quite markedly, especially relative to methane. So what that means in that effectively, when you circulate to surface in oil-based muds, you're going to retain the C2, C3, C4, C5 components. So you have to make a correction as best you can for those. Now, in an ideal world, you'd sort of do a PVT experiment, yeah. And you'd take your mud, you'd put some stuff into solution, and you'd work out how much of that material comes out of solution in a typical sort of gas trap type environment at different temperatures, and you would correct your muds accordingly. Now, that is what some service companies do. So if you get some of the high-end systems, they will in fact do that for you. But you can also just look at some simple literature-based ones. So I've looked at some literature-based solutions here. So this is where actually people have done PVT experiments and looked at how much is liberated from muds. And then I've also looked at MDT samples. So if you want, you can do a little local correlation. So I've looked at MDT samples and the Wellsite gases at the same depth, and then just applied the correction factor for those. So I think Lloyd's sort of doing something in the North Sea where we've done that. And the sort of 4 graphs that I've given you there give you an idea of what it is. Interestingly enough, what you find is, if you sort of look at that, is that ethane is relatively pretty much the same in the mud as it is in the reservoir fluid samples. And what you're trying to do here is basically get to a reservoir fluid composition. So this is what you're ultimately trying to do. So C2 is pretty much the same. Methane's enriched by anything by sort of 5 to 15%. C3 is usually depleted by around a factor of 2, but it can be anywhere from about 1.5 up to about 4. C4 is depleted by about a factor of 3, and C5 will be. It wasn't enough data to do C5 in the data sets we had, but C5 will be even more depleted. Okay, so you need to take those into account. So if you look at the program, these are built in as a sort of a reference, what we call an EC. So it's an extraction efficiency coefficient, and that allows you to correct for these. So that'll automatically multiply your gas compositions by the relevant number. Yeah. So you can use gases to spot pay. They're really, to do that, what you've got to do really is decide what volume of gas is associated with a typical pay. Yeah. And ideally, what kind of volume of gas above what would class as an anomalous? I mean, obviously it's going to be a high gas value. What would be an anomalous value? So what would be a value that's an anomalous over a background that would be indicative of pay? So a couple of things there's various methods to do that. We've looked at just totally plotting up the distribution of all the total gases and looking to see where where you get a bend off a sort of standard distribution. So you can do them as histograms. We've looked at rates of change of gases when we looked at frequency plots. So there's a variety of ways you can do it, but the simplest one often is just to take a background gas in a mudstone. So here you've got on the gamma ray, you can see there's a section with high resistivity and low gamma ray. So those are sands probably with pay in. We've marked off. So what you can do is you can take those values from the shales in between those, or from nearby adjacent shales, and get some idea of what a background gas value would be. And what we did, what I've done and what we've done with the APT, and sort of what I've done through my experiences with Wellsite gases, is then just say, well, okay, if I get this background value, what value above the background is typically indicative of pay? And we come out typically with a value of sort of 3 to 4 times the background value is indicative of pay, is a good discriminator of pay. So it works to spot about 80 to 90% of pay in most situations. So that's a good discriminator. So we've stuck with that relatively simple approach in the program. And the other thing that does is, if you like, is because you're measuring the background gas and the anomalous gas with the same detection extraction setup, in a way that takes out some of the inherent errors between wells. So when you look at wells, it's very rare you're going to find exactly the same gas values from well to well. They vary, and they vary for a variety of factors. I mean, where you place the sensors, how much of the how much gases are lost upstream of your sensor. All sorts of things can affect gases. So this, in a way, is a way of sort of taking that variation out. And I've just put a little example there. So if you've got a background of 0.4 and a gas value of 1.6, then that gives a number of 4. But the same would be true for a background of 1 and a gas value of 4. And in fact, in the program, that sort of gas divided by background gas is called anomalous gas, and it's one way we think we can compare it both within and between wells. So that's a sort of useful thing to do. And obviously, once you've done that, your gas is measured per unit per unit of depth. It's usually half a meter. Well, it's usually a foot or half a meter. So obviously, what you can do is you can do a simple pay calculation by just summing up all those intervals that have that sit above your pay threshold and then totaling them up. So you can work out a net pay if you like. And so on the plot there, you can see that's what we've done. The little green markers there on the calculator pay, they mark up where we think there's pay. And on this one, we've sort of looked at the petrophysical pay, but petrophysical pay on this is a very sort of broad classification, so you don't really distinguish. But what you can see there quite clearly is that your pay zones are matching up with those high resistivities, and you're sort of matching them down well. And interestingly enough, you can also see that your bottom of your calculated pay also sort of is concurrent with where the oil water contact is. So that's quite a nice well. That's a sort of well out the North Sea. Yeah. Well, what causes so the other thing to sort of think about is, well, we're sort of measuring. So the total gas is pretty understandable. You're just measuring total amounts of gas and you're relating those to pay. So that's pretty straightforward. But what's causing the change in the composition was, well, what's changing causing the change in the gas composition going to the mud is really probably related to the maturity of the source that you're looking at. So so typically, as you sort of think about what happens to a typical sort of source rock or any kind of organic material in a rock, then the first thing that usually happens is you're going to generate some biogenic gas, and that's typically more than 99% methane. It's usually more than 99.5% methane. Sometimes has a little bit of ethane in. Sometimes has a little bit of propane in, but it's very rare it's got propane. It's quite common that you'll see biogenic ethane, but only at very small amounts. As you start to generate oils, then you also start to generate associated gases, and those associated gases usually start off as being relatively wet, so they contain a high amounts of C2, C3, C4, and C5s, and C8s and all the rest of the compounds up, relative to methane, and they usually contain, say, more C3 relative to C2 and C4 relative to C3 and C5 relative to C4 as well. Now, there is a little bit of a complication often at the very early stages of oil generation, in that if there's any biogenic gas trapped in your pore system when you first start to generate oils, then often if you've got a good oily source rock, the oils that you generate are going to be undersaturated, and they often take a lot of that biogenic gas into solution. So one of the things you might have to think about if you look at low maturity oils is they might actually look more methane rich because they've got biogenic gas in which case you might have to use the indicators for GOR that just use methane versus the thing might actually make them look more gassy than they are. In which case you can use things like the C3 divided by C2 plus C3 and the normal divided by normal plus ISO C4. Now, as you progress, then, as you get more and more mature, then generally what happens is you generate much more methane, so your wet gas concentrations go down. and the amount of C3 relative to C2, and to a lesser degree, C4 relative to C3 and C5 relative to C4 go down. Yeah, so you basically skew your distributions. A little plot on the right hand side is what we call a malarogram. So that just plots a distribution in log terms. So it's a relative concentration in the log sense of the C1 to C5 components, and you can see there the areas in green are oils, and the areas in reds are gases becoming, as you move from the sort of dark red to light red, you're becoming progressively leaner, CGR-wise. So by the time you get into the bottom of that light red zone, you're into dry gases. And then there's also marked on biogenic gases on there as well. So you can see there, you know, that gives you some idea of what the relative concentrations are. So you can see quite clearly on that, you know, C3 is going down relative to C2, and the wet gases are all going down. Yeah. You'll also notice that normal C4 goes down relative to iso C4, and the same thing with normal versus iso C5. So these ratios are probably related to maturity. Yeah. So in which case we can sort of take a look at them. Now, the easiest thing to relate gases to is to relate them to gas isotopes, and gas isotopes show a pretty systematic change with maturity. Yeah, so essentially biogenic gases, very characteristically isotopically light, and then as you generate thermal gases, you go from light isotopes to heavier isotopes, and there's lots of literature that will allow you to look at that and relate it to whichever maturity you want to relate it to. So you can relate it to an RO, for instance, or you can or a thermal stress type indicator. So what I've plotted up here on the left-hand side plot is really just C3 at the top. C1 at the top. Sorry, my eyesight is getting worse. And so methane versus the fraction of the C2 to of the C, you know, of the total gas distribution. So it's really the fraction of methane, if you like, which we would call dryness. And then on the bottom one, the fraction of C4 relative to sort of C1 to C5 gases. So these are, if you like, if you summed up the C1 to C5 gases and then looked at the fraction of C1 as looked at the amount of C1 as a fraction of that and the amount of C3 as a fraction of that, that's what you get. So you can see that, and I've just marked up some sort of RO and sort of STS. So these are sort of standard thermal stress at 2 degrees, temperatures 2 degrees percent degrees, 2 degrees per million years heating rate. Sorry, so sort of standard thermal stresses, if you like. And what you can see is as you get more mature, the amount of methane goes up, and the amount of C3 goes down, and also there's a very marked change, so it becomes really quite a marked change as you start to sort of go out of the oil window and into the gas window. You can also see on there, I've just marked up what unconventional pay does. So that little blue line on the methane diagram shows you basically, you know, if you look at non-conventional pay, then it pretty much follows the same pattern as conventional pay, up to sort of about, you know, somewhere between 180, 190 degrees centigrade, and then 150, I think that is. 180, 190, yeah. And then it rolls over, so the isotopes become lighter again, which just, you know, tell you you're starting to get gas-to-gas cracking. So that looks like that's happening at about somewhere between 180 and 190 degrees centigrade. You can do the same kind of thing with fractions. So I've just plotted up the fraction data there. The common ones we have in the program are C2 divided by C2 plus C3. Sorry, that's C3 divided by C2 plus C3. Sorry, that's my mistake there. That should be the other way around. And normal divided by normal plus iso C4. So you can see basically as you get more mature, the amount of C2 relative to C3 goes up, so that ratio goes down. And as you get more mature, the amount of iso relative to normal goes up, so again that ratio goes down. And you can again, you know, if you wanted to, so let's say you're in you know, you want to, in unconventional world, and you wanted to know an RO for some reason, you could convert these ratios to RO, either by going to the isotopes and then to an RO calculation by the isotopes, or whichever kind of way you want to go, really. So okay, so you can see that they're related to maturity. So you can therefore sort of take these ratios and make some prediction of well, really sort of historically, what people have tended to do is predict what they call a petroleum type, which is really just something that says, well, it's oil, or it's gas. Yeah, there's usually sort of a non-productive category in there. So which is really sort of just small amounts of residual material in there, and you can go through the common ones for these and the ones we have in the program are plots by Whitaker. Whitaker, I think, did his, I can't remember, I think it's sort of 60s, 70s, and Pixler is actually way back. Pixler is sort of a 1950s or early 1960s. So Pixler's just plotting C1 relative to all the other components on a log scale. Yeah, so just the ratios there, and you can zone that then off into non-productive oil, productive gas, and you can see basically, what that's telling you is that as you start to get to gaseous concentrations, as gaseous composition's got a lot more methane in, basically on that plot. Whitaker's plot was had a bit more to it really, because it looks at a series of ratios. So it looks at wetness, which is the converse of, of dryness. So we know that should bear a pretty good relationship to maturity, and it looks at balance, which is really just the light hydrocarbons versus the heavy hydrocarbons. So it's C1 plus C2, divided by the rest of everything. So C to 3, C to C5 in our things, and then they've got a character ratio, which is the amount of C4 and C5, which is is an even heavier end, if you like. It's the amount of C4 and C5 divided by C3. And the nice thing about the character ratio, it's not affected by methane. So things that add extra methane, like biogenic gas, probably won't affect your character ratio. And you can go through. So there's something there from the SPE by McKinney. You can go through, and it's pretty easy to sort out. Gases are usually pretty dry. Oils, conversely, are usually pretty wet. And then there's a sort of zone in the middle where you've got wet gases between 0.5 and 17.5, and where you need to look at your balance and character ratios to sort out whether it's likely to be a gas condensate, or you use a phase separated zone where you're looking at gas condensate or oil and gas. Yeah. So, and so we've kind of stretched that a little bit further, if you like. We've kind of tried to. We've taken the big PVT databases that we've got, and then sort of stretched those to start to say, right, okay, well, what would this mean in terms of GOR? So what I've done on the very right-hand side of the plot is I've just plotted normal divided by normal plus ISO C4, put some relationships, and that ratio is affected by biodegradation. So the only thing you need to be a little bit careful about there is if you've got biodegradation, then obviously you remove the normals out of the C4 distribution, and you start to get very low ratios. And then also I've looked at C3 divided by C2 plus C3. And then we've looked at the ones we use in the program is we've more than those two. You can use all of these because the technical manual has the relationships in. The relationships for normal plus ISO C4 and sort of C3 divided by C2 plus C3 are not coded into the program, but they're in manual. So if you've got the values, you can abstract them off. You can take the values off the plot. In the program, we actually look at the C1 and the C3 fraction. That's because those are the ones where we consistently got a better fit. So you can make an estimate of GOR. If you make an estimate of GOR, the plot on the very right-hand side is just API versus GOR. And we've annotated that also with cut fluorescence color on the bottom. So if you've got cut fluorescence or you've got a GOR, then you can also make an estimate of API. So you can, take all this all the way through and start to make a forecast of a GOR and API. We don't implicitly make a forecast of API in the program. We do GOR, but we don't. There are potentially complications with this when you look at phase separation. And we think that probably, if that redistributes the methane, for instance, more into the gas cap than the oil leg, then, if you might encounter fluids that start to look more methane rich, but in fact quite low maturities. So and also if you start to get GORs predicted, so these are probably GOR predictions. So the best way to think of these are GOR predictions where you're in a system where you can't phase separate. So you'd be in a supercritical fluid, so high pressures and high temperatures. If you bring the sort of areas that I've shown in yellow and orange to surface, and you bring those kind of compositions up to low pressures, they will phase separate. So they separate off into a gas cap and an oil leg, and then the GOR really becomes pressure determined rather than fluid type determined. So there is sort of a complication here that you need to sort of make an estimate of if you're putting these in low temperature and pressure regimes, you might need to do a cross check with something like a Girasol equation and see what a typical maximum GOR might be for a fluid. We're also sort of thinking that you might see inconsistencies between, so often in these kind of circumstances we think that the sort of ISO, the things that separate less, that are less likely to sort of separate into gas cap and oil leg, would be closely related, molecular weights that are close together. So the ISO normal C4 ratio, and to a lesser degree the C2 versus C3 ratios should be better. And often what we think we see is they give a better prediction of a GOR in these kind of systems, because the methane often tends to get distributed between the gas cap and the oil leg. So bear that in mind. So it's not always, so you might need to just do a cross check if you think you're in a phase separated. So if for instance, if you're C3 or C1 thing is giving you a GOR of sort of 2.5, 3,000, it's very unlikely at pressures much less than about sort of 6,000 or 7,000 psi that those will stay as single fluids. The manual does have some description of simple phase diagrams in, so you can look at those if you've got nothing else to guide you. They're based on Girasol's equations and then William England's predictions for CGRs. So if you've got nothing else to go by, those are a good rough start as to what sort of GORs and CGRs you might end up as. Okay, so I'm hoping that you've all sort of got to this place now, and you are going, oh yeah, I realise that we can look at amounts of gas and they should be related to pay, and so provided you've obviously made the corrections for drilling parameters, and you've done some sort of background type analysis, so you're relating them, so you can make an estimate of what the background is and then use a value above that. And obviously, if you can spot it, you can make an estimate of thickness. So you could do a net pay, for instance, in a zone. It would be pretty straightforward. Yep. Background gas value, well, that sort of gas divided by background gas, which we call anomalous gas, we think that might help us correlate between wells and correlate within wells. And so obviously, if you want to look at petrophysical pay, if you want to relate this to, say, density or oil saturation or hydrocarbon pore volume is what it should reflect more than anything else, then that sort of gas divided by background gas, so anomalous gas value, is probably the one you should use rather than just the normalized gas. Certainly if you're looking between wells, you can still do normalized gas in a zone in a well, but if you're starting to look between wells, I'd advise you to look at this anomalous gas value. You need to correct for all base muds, and we think the gas compositions are related to source type. Source type is probably less of an issue. Source maturity is more. What tends to happen with source type is often that if you've got a Class D, for instance, relatively, sort of medium HI, then what it'll do is it just tends to liberate its oil and gas later, and a sort of a classic sort of Class F Coley source, So these are BP classifications, by the way. So Class F would, I suppose, be 3 to 4 on an IFP classification, and a typical marine oil source, usually Class 2 rather than Class 1, but Class 1, Class 2 sometimes. So so what tends to happen is if they're lower HI or Class F, they just release material later on. So they tend to start off drier, and you know, they start off with more methane in, and they start off with less C3 relative to a smaller C3 fraction. So if you like, you can just think about progressing the classes, and if you do it on isotopes, you can do a nice discrimination between classes and their isotope values. Okay, historically that's been used really just to sort of say, is it oil, is it gas and oil? We're kind of making a bit more of a push to sort of give an estimate of GOR. And the reason we like to do that is because from an engineering point of view, once you sort of get a GOR and an API, you get to what's called a formation volume factor. Formation volume factor is the what you need to multiply, you know, what basically tells you how much surface volume you get for of oil you get for a subsurface volume of oil. So you can start to get to things like, you know, how much gas am I going to produce at surface? What's the formation? What's the what reserves of oil? So you can start to get to sort of reserve numbers, and also you can start to think about what would be typical viscosity of the fluids in your reservoir. So you can, so if you've got, you know, you can start to make estimates of, well, how likely is that I'm going to be able to produce this kind of stuff given the reservoir quantities I've got. So it works it more into an engineering type sense for fluids. Right, where can it go wrong? Well, it's like everything else, it can go wrong. Everything can go wrong. Petrophysics can go wrong. Geophysics, we all know, can go wrong. So there's nothing in looking or developing oil and gas that is 100%. So probably that's the first thing to remember when you think about this, is just bear in mind that, you know, other people might go, well, you know, it's a really shaky technique. All techniques are shaky if you sort of look at them in enough detail. So well, you know, let's not go down that path. So the key issues really that make them not related, or things that really make them not related to the rock volume drill, or put them in the wrong kind of, depth placement, yeah. Or things that you sometimes lose at surface. So if you've got, you know, really bad systems, you might just lose a lot of material at the surface. And so we'll just work through those. So gas that are not related to rock volume, they usually come in two sources. Well, usually come in three sources actually. So a couple. So if you drill under balance, then obviously you can get influx. You'll often see that as connection gases. But if you stay under balance for any length of time, you do actually bleed material constantly into the wellbore. And so long as it's not a big influx, it's, you know, it has to be a big enough influx in a small enough of time that you'll see it in the pit volumes at surface. Because the way you usually spot kicks is you spot an anomalous flow back to surface, so you get a pit gain. You very rarely you'll see, you know, you have to have a good setup to see pit gains of much less than a barrel. And obviously, if it's a barrel over 10 hours, you're not gonna monitor it. You know, if it's a barrel over 5 minutes, you'll see it, but a barrel over 10 hours, you just won't. So what that'll often do is it'll increase your background gas values, because you, especially because you just take, especially in oil-based muds, because you just take more and more gas into solution in the mud. Yeah, you often still see detail on top of the background, because obviously if you drill through something that's got high hydrocarbon saturation, you know, it'll boost it even further, but it causes you problems in the background values. So and you'll often see that as, you know, sort of continual change in background gas values. And the classic one is when if you raise the mud weight, those background gas values go down, because you effectively stop the flow into the well. If you drill close to formation fracture pressures, then you can initiate fractures. And formation fraction pressures are a bit of a complex beast, because normally in most circumstances they're related to the amount of overburden. Obviously stress, you know, if you're pulling a basin apart, then your fracture pressures will tend to be a little bit less than your overburden. So, you know, you're putting tends, you know, sort of effectively trying to pull the basin apart. Similarly, so if you're compressing it, so if you're in a zone where you're compressing it, your fracture pressures might be actually higher. If you start to get weak rock, then, you know, you'll also see fracture pressures as lower. So and also, if you think about it, when you're drilling a well, you're often circulating cold muds down a well bore. And so effectively what you're doing is you're causing thermal contaction in the near wellbore, and that again can open up, can help open up little bits of fracturing. So if you're looking at really cold muds going back into relatively hot formations, then you often, you know, you can put quite a lot of thermal stress on the wellbore, and you can get a fracturing that's initiated because of that. So it doesn't. So you usually measure fracture pressures by leak-offs, but obviously you only usually measure leak-offs every time you do a casing, so you don't necessarily measure it all the way down the well. So just be aware it can be a number. It's often quite close to overburdens in most of the basins we look at, but it doesn't have to be. It can be quite a lot of things. The other thing you can do, if you start to get washout or over gauge hole, then effectively what you're doing is, for the normalization calculation, if you think, what you're actually doing is now you're adding more sediment in. So your gases will go up, but you won't recognize that because you're stuck with a certain hole size. And often over gauge and washouts, you really won't see those until you've done the whole section, because it's not really until you get a caliper log that you kind of understand, you know, how out of gauge your hole is. Yeah. That also impacts on the next one, which is depth displacement. The way you place gases into depth is you measure a lag time. So you work out the volume of material you need to pump around down the drill string and then back up the annulus to get cuttings from a depth back up to surface. And obviously the way you do that is you have a series of hole sizes, and you've got the sizes of the drill bits and drill collars and everything that you put in the wellbore, so you can do a volume calculation for how much of the wellbore your mud is going to go around. Now that works hunky-dory if your well's all engaged, but if you start to get a lot of washout, so you get very over gauge hole, then what will happen is it'll actually take you longer, if you think about it, because you've got more volume to pump around. So you'll go out off depth. You'll start to your actual gases will be measured at a deeper depth relative to something like a wireline or an LWD that's not affected by hole size. So so that's a problem. Now, if you've got a good muddling company, then often what they'll do is they'll do a lag calculation. So they put something into the mud system that they can then see when it comes back to surface, and then they do, you know, they can correct for that gives them a volume of, they can then, you know, back calculate the volume of material that they've pumped to get round, and that allows them to correct for these kind of things. But again, they don't often happen. That's not something that happens frequently. So it is possible to get things off depth through sort of a bad lag time calculations. The other thing is, if you're drilling, it's usually more in deviated sections than it is in vertical hole sections. If your cuttings, if you don't get proper circulation of cuttings back to surface, so for instance, all your cuttings start to stay in the wellbore, then obviously, then you're not circulating that material back to surface, and it's not losing its gas. And so, you know, if you're starting to not circulate cuttings back to surface, then again, you know, and all of a sudden they come in one big rush, which is not uncommon. Then obviously you'll get a big problem with where that gases are placed. Yeah, losses of gas on the surface. Not really one that affects you too much, but what you'll often see is that if you look at connections, you'll often see sawtooth gas data, where you get very low amounts of gas after you've sort of made a connection, or you've stopped circulation for any reason, and that just basically says, you know, what that is it's your surface plant, if you're degassing at surface, and obviously the longer you leave it, the more it'll degas. And that usually shows up as a sawtooth profile, so low amounts of gas as you start your circulation up, and those gases are often wetter. Excuse me, because you lose your methane in preference to your ethane, propanes, and so on. Okay, so that's pretty much the sort of the theory side of it done. So just look at some examples. So this is the one we showed earlier on. So this is a nice conventional pay. I've just marked the pay zones on. You can see we spot all the nice resistivity peaks in there, and you can see actually on the compositional data on the Whittaker plot, then you see a transition from gas condensates through to volatile oils, and then through to oils as you go down through this accumulation. Yeah, and so things in your oil leg tend to look oily. It does look to be a bit of a transition zone around the gas oil contact where things are looking sort of like really volatile oils or very, very rich condensates. And then as you go into the gas, they look more like gas condensates. So here's just the same kind of thing, but now we're just sort of doing the sort of we're looking at these GOR plots that we've got and the malariograms. So I've just taken a couple of malariograms here out of the gas cap, which very, very nicely for us to look like they're gas condensates, and then a couple in the oil leg which look like they're oils. So, and you can plot them up on your C1s and C3 fractions. So I've just marked them there. Oil leg gives us something about a median on those gives you something about 1,000 standard cubic foot barrel. Gas cap gives you something like 15,000 standard cubic feet per barrel. You'll also note there's one right in the middle, and that's there's a little transitional sand in here. It's actually the one on here just below the gas oil contact. And that almost looks transitional, and that it's not uncommon that happens around gas caps. Actually, what's happening around gas caps in fields is usually molecules are transitioning backwards and forwards between the gas cap and the oil leg, especially if you think about it on a geological term, because you're usually changing the composition of what gets accumulated. So if you think about it, if you just follow the transition through in an oily basin through from an initial light oil, initial sort of low GOR oil, and it gets higher and higher GOR oils, then it'll phase separate, and then as you keep adding the gaseous system, then the lighter components are going to sort of make their way through the oil leg and into the gas cap, and so it's a constant dynamic situation. It's very rarely static, and so you often get these little transitions around gas oil content. You sometimes get really, really weird fluids. You'll often get sort of things that are higher API, and they're sort of they're oils that are trying to be gases or gases that are trying to be oils. So it's not uncommon in these circumstances. But that worked pretty well on that well. And here's just the CPI. So this is a sort of classic CPI. So CPI stands for computer processed interpretation for petrophysics. It just means that you've run this through Archie equations, or you run it through, you've done your V shales, you did all the things that petrophysicists would do to basically, and basically what they're trying to derive is, at the end of the day, is a porosity or an effective porosity. So porosity that your oil volume sits, or your gas volume sits in, some idea of a saturation, so how much of that volume is saturated with oil or gas. And a permeability. I mean, that's primarily what they're trying to get at, because those are the things you need to do to be able to model the flow out of the unit. So you can see there, we've done pretty well. It's got a gas cap, and the gas cap's pretty rich gas condensate, and the oil leg is it's 1,080 GOL. So I'm going to forgive it for being slightly too rich relative to our medium, but that's pretty good if we can get that. They don't always work this well, I have to say. So just bear that in mind. And we calculated there's about on the well there on the CPI log, there's about 36 feet of what they call net pay. So that's effective. That's pay that they think they can produce out, and about 60 feet of sands with hydrocarbon saturation. And I think from memory, the pay calculation from the gas data was about 45 feet. So we're in the right kind of ballpark. Here's another one. This is a well. So this is quite a complex series. So here we've got a well, nice big thick shale on the top, and then you go into this really very thinly bedded sands and shales. Some better sands in it every now and then. Quite resistive, some of them. So you can see that some of them look like they've got indications of pain. Although this is a freshwater system, so again, in the freshwater systems, your resistivity, because the freshwaters are actually quite resistive relative to saline waters, they're often not as so the difference, if you like, then between something that's got oil in it and saline water is you get much more contrasting resistivity. Whereas if it's a resistive fluid like oil and more resistive water, so fresh water, it's less of a difference. So it's not necessarily always as easy to spot off resistivity as you think. And I've just plotted up, so you can see there lots of indications of pay. If you sort of take a background in there, about sort of 0.5. and those and then you can see that some nice, all looks reasonably high C2 C3 ratio, quite wet. And you'll also note that the wetness sort of varies down the well. So in fact, actually, as you come towards the bottom of the well, below 2,400 meters, sorry, then it starts to get wetter, which is quite interesting. And I've just done some compositions and some sort of GOR calculations there for A, B, and C sands and D sands, and you'll see they're all pretty. They all look pretty oily here. So they're all sort of GORs anywhere from about 300 to probably about 900 ish. A little bit more variation in the D sands, and the variation primarily in the D sands is actually at the very top of the D. So it's in that little zone. It's in the sort of D2 sand. The rest of the ones further down look much more oily and look similar to the sands that you see at the top. In fact, if anything, they look slightly oilier than the sands at the top. So this was a suite of 4 wells we did I think we did this for a client, and we looked at 4 wells. Well, we did do it for a client. So we looked at 4 wells, and they gave us all petrophysical data. So they gave us the petrophysical data that effectively gave a porosity and a hydrocarbon saturation, and also a permeability. So permeabilities here, I think, were they were NMR derived permeabilities, although they'll be backed up with core correlations, I suspect. So you can see it's pretty good correlation there of where we see pay relative to where the logs see a hydrocarbon pore volume. You'll see it's actually pretty low permeability pay, a lot of this. I've just done a little cutoff value there at 1 millidarcy. So a lot of the stuff here is less than a millidarcy. There's not that many zones that are a millidarcy plus, and there's sort of highest permeabilities are 100, but more commonly sort of the tens of millidarcies. Interesting enough, on this particular well, if you just do a cross correlation, you see how much of the pay that's greater than 1 millidarcy permeability, then the gas data spots 3/4 of all the pay, slightly more than 3/4 of all the pay. On the 4 well study, when we looked at all 4 wells combined, then if you looked at any permeability, and just so anywhere that's just had the hydrocarbon pore volume in it, then the gas data would spot 70% of that. And if you put a cutoff at 1 millidarcy, then you'd spot 85% of everything that's greater than 1 millidarcy that had hydrocarbon pore volume. Now, these are such low permeabilities that there might be a bit of debate about how good the logs are here. So those are numbers just assuming that the petrophysics is right, but obviously the petrophysics doesn't necessarily need to be perfect all the time. So, but pretty good. I mean, I'm not going to be too worried if I spot sort of 85% of all the reasonable pay. So just a little note here. This is sort of just looking at shales and sands, and I think this is looking at the same well actually. So you often see a difference between data in sands and data in shales, and there are sort of good reasons for that. If you think about it, what you're typically looking at in the sands are usually, not always, but usually low TOC. Usually what you're looking at in sands is material that's migrated into them. Muds are different. Muds, you can invade a mud, but it requires a certain amount of hydrocarbon column to do it. And even if you did invade it, it's very unlikely you're going to invade a big fraction of the pore volume, because the pore volume distributions typically in mudstones, there's always a certain amount of pore volume that's just too small to really be invaded unless you've got really, really big, columbites to give you enough pressure to get into them. So what that means is that in a mudstone, you're going to see some volume that's got gas in that might come from somewhere else other than migrated gases into the system. So it could either be sort of biogenic, if it's got dispersed organic material in it, then the dispersed organic material won't necessarily won't necessarily distribute itself as permeability, so it'll be distributed through the rock. So it's going to put material into some of those small pore volumes that you might not invade, and that could either be biogenic gas if it's low maturity, or if it's high maturity, it could just be it can just be in situ gases that are generated. So in this particular one, if you look at it, the mudstones all look a little bit drier. If you do very detailed isotope work, you can often see this. but you have to do enough isotopes in the sands and the shales to be able to distinguish the sands and the shales, and there just isn't enough data. The little brown points on the plot are where the isotope data is, and you can see there's really not enough data there to sort of be able to accurately characterize sands versus shales. Partly because this is such a thin bed system. So another thing to think about is, if you're going to do isotube or isotope programs, this is one of the things to think about. You need to collect enough isotopes. You need to collect enough isotube data that you can distinguish the two, because you might get a different answer from muds than from sands. There's the isotope data. So this is now using the sort of program's ability to look at isotopes. So what I've done here is I've plotted all the gases. I don't know why I've plotted all the gases on the total gas plot, but you can plot the total gas data onto the gas plot, which is quite nice. So you can see, where does my isotope data look the same as my Wellsite gas data. I've plotted the ratio data onto the ratio data on the sort of gas plot option that you've got. So you can see there the ratio data from the isotopes. The ratio data from the isotubes looks pretty good, actually. It looks like it matches up. The dryness, the C3 divided by C2 plus C3, and the C2 divided by C2 plus C1, which is the sort of green and orange curves. I didn't do one for the normal divided by normal plus isobutane, largely because it kind of obscures the dryness data, but it does sit on top of the plot. The other thing you'll see now, which is quite interesting, sort of looking at the gas data, you can see as you go at the bottom of the well, your isotope values become isotopically lighter, which would suggest, well, possibly one or two things. It would suggest there's a couple of stages of migration. You've maybe migrated a more mature fluid through, and now what you're doing is following that with a less mature fluid from a different source. That's one option. Or the other option is you've actually started to do in situ generation at the bottom of the well. So now what you're looking at is a small amount of low maturity in situ material being added. But either way, it's going to affect your overall compositions, and you can see it does. It affects the dryness both in the sands and the shales, which might suggest it's more to do with migration than it's to do with in situ. And so you can see that quite clearly in the methane and ethane isotopes, less prominent in the propane isotopes. You can also see here that you've actually, we didn't do a lot of gas isotope data in the top seal here, but you'll see in the top seal, you clearly migrated C2, C3, and C4 pretty much all the way through that top seal. So you can see dryness does decrease, but the thermal gas is pretty much all the way through. And in fact, there is a small, really biodegradable oil accumulation further up at the top of this well. I'm not sure exactly if it's related to the hydrocarbons you see in the bottom handle section, because I don't know if we've done work on it. But there are accumulations above that shale. Okay, so here's a sort of non-conventional pay. So this is a well out of the Permian Basin in Texas. The big sort of this is a vertical well that was drilled before the company did laterals. They were looking to see they were primarily aiming at the Wolfcamp A and B as their target. And so here's just the gas data for the well with the logs and the compositional data. So you can see there we pick up a little bit of play in the Lower Strawberry, and in fact they did test the Lower Strawberry in one of the laterals, so they did get a little bit of oil out of the Lower Strawberry. And you can see there's a lot of pay there associated with the Wolfcamp A and the Wolfcamp B. Interesting enough, the reason the normalized gas gets quite higher in the sort of Wolfcamp A is because they drop the flow rate in the Wolfcamp A and the Wolfcamp B, so you're getting more gas into a smaller gas volume there relative to the Wolfcamp B. But Wolfcamp A and Wolfcamp B both showing good pay. And you pick up little bits of pay there in the Wolfcamp D as well. There is some pay at the very top of the well. Julian shows me that is sort of really is a typical sort of tight sand pay, but it wasn't really primarily what we were looking at here for this particular operator. And you can see if you look at compositions here, really quite oily, yeah. So in this one I've just sort of predicted a GOR, a vitrite reflectance, just to sort of, so if you're looking at if you're sort of more used to vitrinite reflecting, this is what they would be. So they're going to be, you know, if you're thinking about this, then obviously it looks like we can spot where the pay is, but it also looks like we can spot what's the composition. The composition is actually quite useful for non-conventional pay because you know, you're looking at things that are really low permeability, and you need all the sort of viscosity help you can get in a fluid. So generally, things that are less viscous will be easier to get out than things that are more viscous. So these are going to be, in the grand scheme of things, these will probably be sort of, I think they're mid 30s API fluids, but they're, you know, not going to be as low. They're not going to be as low viscosity as something that might be, say, a couple thousand cubic feet per mile. Yeah. Here, we obviously haven't really done a tremendous amount of conventional play. So what I did here was just have a quick look at some North Sea Kimmeridge clay examples. So this is a North Sea Kimmeridge clay in the central North Sea, where the sort of Kimmeridge clay at the top starts off about 155 degrees centigrade. It's about 175 degrees centigrade at the bottom. It goes into Fulmar sands at the bottom. You can see there the Fulmar sands, interesting enough, here don't look like they're in pay. There's no pay indicated. And there's quite a lot of connection gases in this section, especially below about sort of 15,600-ish feet. You'll see there's quite spiky data, and you'll see we've marked in the warnings there where all the connection gases are. So you can actually see, you know, quite a lot of those concur with the connection gases. So the pay, and I've just marked up what zones are pay here in the Kimmeridge clay. So you can see that, you know, if you sort of did a background at about sort of 0.05 here, then you'd end up with quite a lot of pay in the top part of the Kimmeridge clay, less so as you move down into the bottom part of the Kimmeridge clay, although some of that might be because we've discounted for the connection gases. And you can see here there's really quite a nice transition as you go down the well. So as you go down through the Kimmeridge clay, you start off at volatile oils at the top, and by the time you get to the bottom, you're in gas condensate, which would be consistent with the kind of temperature range, you know, if it was in situ generation, it would be consistent with the kind of temperature range that you're seeing. Now, the other thing I did here is I just sort of took this and related the, I mean, here I've just, because it's all in one zone, I've just related the normalized gas, so the composite normalized gas. You can see there's quite a good, so a couple of things on these plots. Anything sort of above 4 or 5 on these plots tends to be the connection gases. So you can see that if you sort of exclude that data, then there's a pretty good relationship to uranium, which tells you there's probably a relationship to TOC, because uranium is very likely to be related to TOC. And this is a much better relationship to density. Now, density here, obviously, so densities really measure, you know, it can measure a variety of things. Could be increased porosity. More likely that it's increased TOC here. And so, you know, but again, if you're looking at density in a non-conventional sense, then you would look for lower density. Lower densities would tend to indicate more organic material, but also they could indicate more porosity or more organic material with organic porosity, essentially. So there's some. So you can, you know, you can sort of take this and relate it to petrophysical properties. This was quite a nice example of that. Okay, and yep. So we primarily at the moment, the sort of tool is designed to look at spotting pain, compositions in pain, but you can also use gas data to look at pressures. So this is another well from the North Sea, from the central North Sea. What I've done here is I've got a total gas plot. On the total gas plot, what I've done is I've used, it took us a while to sort of have a light bulb moment, but we realized that if you've got compositional data and data for the, or just total gas data for the connection gases, you can just input them as isotube data. Yeah, so you just give them the depth and a total gas and a composition, and you can plot them in. So on this particular well, we didn't have compositions, but we did have total gases. So some interesting things as you sort of come down. So and so what I've done is I've given you a resistivity plot, and the far right hand plot is a pore pressure plot in pounds per gallon of what the so it's got hasn't got the actual pore pressure for the well on. I've sketched in what I think the pore pressures might be in the dotted red line, and I've put in an overburden in blue and a sort of clay fracture pressure in the orange, and then you've got an ECD and the static mud weights in there. So the ECDs are the ones that are sort of green that look higher than the static mud weights, which I think are in blue. So you can see as you come down the well, you get to about 12,500 feet. You see your background gas increases, yeah, and your connection gases increase accordingly. And there is a bit of a drop off in background gas at around sort of 13,300 feet, but your connection gases actually stay high. You raise where I put those blue lines across is where there were sort of significant changes in mud weight. So you can see as you change the mud weight there around 13,600 feet, your background gases and your connection gases drop off. And then there's a really, really rapid transition as you come into the Valhalla, top of the Valhalla. So your background gases increase quite dramatically again, and your total gases, your gases that you see on connection, the total gases increase really dramatically. So now they're going up to 25%. And you can see then they actually took a kick at around that depth, or took an influx, and so they raised mud weight quite rapidly. And you'll see the background gas drops off, and their connection gases drop off. But you see they don't actually drop off all the way back down to low values again until you actually set the casing in. So you probably never got this well back to balance properly until you actually set the casing, and you bump the mud weights right up to about 15, I think about sort of 15 and a half, 15.9 ppg. And then you'll see you drill down through the rest of the Valhalla. Total gas connection gases are quite low. You drill into the Cambridge clay, you still see connection gases, but they're not significantly bigger than the values of the background gas, and the background gas stays relatively flat. Yes, so there's no big increases in the gases, or a little trickier to say in the Cambridge clay, because the Cambridge clay obviously might, the way the gases fluctuate might be related to organic carbon. But what you do see is as they raise the mud weight around 15,500 feet, then you all of a sudden start to get really high connection gas, total gas values relative to the sort of normal formation gas values that you see in the Cambridge clay. Now that's kind of interesting, because that's the flip of what you're seeing further up. Now, if you're in a zone where you are initiating fractures, so this is so if your mud weights get high enough to your fracture pressure, then you initiate a fracture. When you flow back from the fracture, you flow, because the fracture is actually sort of equilibrated with gases over a much bigger volume than the hole size. Then you get a connection gas which is higher than your background gases. You often also see that it's drier, because if you think about it, what you've put into your fractures is a pressure that's much higher than, it's usually higher than your formation pressures. So the way that the gases are getting into the mud system is probably by diffusion into the mud rather than by bulk flow. And when you raise the mud weight in these kind of circumstances, you just push the fractures further out. You're just actually making life worse for yourself. And you can see that that's quite a nice example there. You raise the mud weight, and sure enough, all the connection gases went up. Yeah. So that's a nice example. So we probably will at some point develop a screen that does this. We've just got to think about how we set the screen up, but most of the screen is there to do it. Really, we just need to sort of be able to take in operators, pore pressures. We already take in ECD and mud weight, and we just need to be able to take in an operator's fracture and fracture pressures and overburns. And this is a nice example. Lloyd will be familiar with this one. So this is an example where we actually have got compositional data for the connection gases. So this is a well west of Shetlands that was drilled, and you can see on the very right hand side, I've just plotted the mud weight. I haven't got an overburden for this one. I've just plotted the mud weights, and you'll see there's a series of little orange dots, which are the formation pressures in the reservoir section where you can measure them. And you'll see that it was drilled, especially sort of below about sort of 8,500 feet. It was drilled quite significantly overbalanced relative to formation pressures. Yeah, so you're probably about a pound overbalance in static. So at the, when you've not got the pumps on, and you're nearly 2 to 2.5 pounds overbalance where you've where you've got the where you've got the pumps on. Now, a couple of things happen in this. Number one is that if you're looking at relatively permeable pay, then you run the risk that you might just push the gases out of the formation when you drill it. And in fact, on this one, we really didn't see a good response in the pay that we know is there in the Colossae 1 and Colossae 2 sands. But the other thing is, if you look at the connection gases, you'll see that, again, I plotted on the total amounts. You'll see in the top section, really sort of in the boulder and above, the connection gases are really like the formation gases. Yeah, so they do stand out as peaks, but they're not that different. Same is true to some degree through the Hildesay sandstones. But when you start to get into the basalts and colza, you'll notice that the connection gases are all high relative to the sort of typical formation gases that you've got. And the other thing you'll see as you go down the well, so in on the sort of middle plot is just the ratios, and then on the sort of right hand plot for the compositions is the actual fractions. So you'll see that as you go down and into these basalts, your connection gases are drier in the background. Yeah, so those dots that are just sitting to the right of the dryness curve. Yeah, you'll see that your normal plus normal iso-C4 pretty much the same, but that's kind of what you would expect, really, because if this was a diffusional process, there's almost no diffusion difference between normal and iso-C4, whereas C1 we would tend to concentrate in the mud relative to C2 and C3, and you'll see that C2 is concentrated relative to C3, so the C3 ratios, the C3 plus C2 plus C3 ratios all come out as a lot lower. And that's also true but to a lesser degree for the C2 plus C1. And you can see it on the fraction data as well. You see the methanes is a little bit obscure on this plot because obviously I've tried to get everything on and it's a log plot, so you wouldn't really see a difference here. But what you'll see is as the molecular weights get higher, they get increasingly further away from the typical formation gases, the connection gases. So this is really quite a nice example of what's probably sort of diffusive flow. And so this is telling you what you've done here is you've actually got fractures. You've initiated, probably initiated fractures. Your fractures are then flowing back to give you these connection gases. And your connection gases, because they're picking up gases by diffusion, are all enriched in methane and lighter hydrocarbons relative to heavier. So that's quite a nice example. Right, okay, so we're at the end. So what I hope you've kind of seen is, these Wellsite gases, you can do quite a lot with Wellsite gases. It always amazes me how much you can do, and you get them on every well. You do have to pay for them, but in general, you won't have to. If you're a geologist, for instance, or an operator, you're going to get these because they are part of the safety requirements for most wells worldwide. So I don't know of any circumstances on a well where I can think of where you've not run a gas system, because you need to monitor gas at surface, and also, as I've shown you, it's really quite useful for pore pressure evaluation. So you're always going to get it. Yeah, you might not always get logs. You certainly won't get logs continuously all the way down a well bore, and you will get Wellsite gas data all the way down a well bore once you've started circulation to surface. So you're always going to get a bigger distribution of the geology covered by Wellsite gases than you do by electric logs, or at least electric a wireline switch with electric logs. You might nowadays get as much LWD as you get gas data, but that's not the case in the past. And certainly, if you go back 20 or 30 years ago, then LWD was nowhere near as good as it is now. Yep. So, and also, you're never going to do. You're never really going to do a wireline run all the way down a well that tells you about a fluid variation. So it's the only continuous record that you're going to get of fluids all the way down, and it's the only detailed record, because even when you do a wireline sample, you're only going to get a fluid composition where you've got pressures or you've got fluid samples. You can see that the relative amounts probably reflect hydrocarbon per volume, so you can invert back if you wanted to hydrocarbon per volume. So you could, if you want to, derive a hydrocarbon per volume out of these, and then you could match that up against your petrophysical data, and you could use it to as an adjunct to your petrophysical analysis to give you an idea of where your petrophysics might be working well and where it might not be working well, and vice versa. And obviously you can do that at different levels of sophistication. And I've kind of shown you that you've done that, and they're going to be really amenable to where. So it's just like petrophysics. Petrophysics gets better as you go through appraisal and development, because you start to relate your petrophysical properties to each other, to core data. So you just build up a much better cross correlation of geological properties and properties from wildland logs, and you can do exactly the same with gas data. Yeah, so they're only going to get better as you go through appraisal and development schemes. And so you can kind of think of them as an extra low-cost petrophysical data, basically. They relate to API and GOR in a well, and you can use obviously variations in ratios and in compositions as an indicator of conductivity as well as an indicator of GOR. So, and especially if you combine that with isotope data and pressure data. So again, it's not just used to predict GORs. If you see, if you saw rapid, very, very different ratios, which would translate to different GORs between segments in a field, then you might suspect there's connectivity issues, and you could check that up with your isotope data, and you could recombine it with your pressure data. So there's really not an excuse not to use them, really, because there's quite a lot in them, and they're so simple to plot up. And this tool does quite a good job, but they're so simple to just plot up and investigate. Okay, so that's it. That's it from me. So Lloyd can stop recording now if he wants. Is anyone still there?
I didn't. Yeah.